Okay, so now we're going to get into a little bit more detail about how it is that this hydrogen ion concentration can change as we go through the pH scale. So we already know that acids have a high H+ concentration in solution, and here we have a low H+ concentration. Okay, and we also know that as we jump up the scale in units of 1, we are changing the concentration by a factor of 10. So on our acid side of the scale, it's quite easy to understand. If you want to increase the concentration of hydrogen ions, you just need to increase the amount of acid that you have dissolved in your water. Okay, because as the acid gets dissolved in the water, it will dissociate, it will separate into hydrogen ions and, in this case, chloride ions. And the stronger you make the acid, the greater the concentration of hydrogen ions. A little bit like making squash. If you want to make really strong squash with a high concentration of squash molecules, you're going to pour quite a lot of squash at the bottom and add less water. Okay, and it's the same principle here. You're going to dissolve hydrogen chloride in water to form hydrochloric acid, and it's going to dissociate. And the more you dissolve, the stronger your acid is going to be. It's a little bit more complicated up on the alkaline side, because you're quite right, thinking about an alkali, for example, sodium hydroxide. When sodium hydroxide is dissolved in water, we end up with sodium ions and hydroxide ions. And you think, well, how does that change the amount of hydrogen ions in solution? And to understand this, we need to know a little bit about water. Now, water is a small covalent molecule. We learned about this in the autumn term. Okay, it shares electrons between 2 hydrogens and 1 oxygen. And I can draw this like that. But it's not quite as simple as this. Actually, what happens is the oxygen here is a little bit greedy for electrons, and it pulls the electrons a little bit closer to itself and further away from the hydrogens, which means that overall the oxygen is slightly more negative than the hydrogens. Okay, just very slightly, and this is called a polar molecule. And what this means is, because this overall molecule has these distinctive charges, we can form very electrostatic bonds between these molecules. And that's actually what gives water all of its properties, which make it so amazing. Cohesion, for example, so when you have a transpirational stream in a plant up the xylem, when it's drawing water up from its roots, the cohesion between these 2 water molecules allows you to have that drag and pull water up, because those molecules are sticking together. Okay. Now, every now and again, what happens very infrequently is that one of these hydrogens can be pulled away, and you end up with something called hydroxonium ion, okay, with an OH. Right? And this acts a little bit like a hydrogen. So these 2 molecules here are, for the purposes of pH scale, are hydrogen ions. So when you add an alkali into a solution of water, where you've got some of these molecules sitting here, these ones in particular, what happens is they will react together, and they will pull these hydrogen ions, or they will react here and pull off one of those hydrogen ions there, which will reduce the concentration of those hydrogen ions or hydroxonium ions in solution. And the more of these hydroxide ions that you add, the more it will pull these out of solution by joining together to form water. And so our concentration of hydrogen ions, or hydroxonium ions, will decrease as we increase the concentration